part of the book, so
Okay.
hopefully it'll be okay.
Uh-huh.
But it's all on. I'm sure that you're familiar with the Stewart book, Single Variable Calculus.
I don't have that one, although I am
Okay.
familiar with it. I've had other students that have it. I'm sure I'm familiar with the principles it's discussing.
Yeah.
But if there are problems that you can verbalize, in other words, if it's area between two curves and you can give me both functions, then we could go from there.
One question I have is, so it gives different ways of finding the area at the beginning of this section. One involving the limit of sigma notation, stuff like that. But then it also has integral notation.
The integral is just a substitute for the sigma.
Okay, so they're the same thing.
Basically, they are. They're defined a little differently. That has to be integrated with respect to one or the other axis. So if I had a function of x inside of here, then this has to be dx. If this is a function of y or some other variable, then it has to be d that variable. In other words, there's no way to integrate a function of y using a dx, not unless you can turn the function of y into a function of x, which you sometimes can do. And then, of course, you go from one limit to another.
Okay.
But the sigma notation, that's kind of trying to get you to understand the concept of adding up the rectangles as
right.
the norms go to 0, or as the width of each rectangle goes to 0, or you could say as the number of rectangles in your interval goes to infinity.
Yeah. Okay.
Okay.
Okay. All right then. That sounds good. And I am familiar with how to do this because I've been doing it over the past few days.
Okay.
Let me see here. I have a few homework problems as well.
Okay. Why don't we have a look at those?
Okay.
You mentioned that you're doing solids of revolution. Is it
right?
Is that what
That's the next section.
That's the next section. Okay.
Right. So that is section 6.1 is area between two curves.
Okay.
Section 6.2 is volumes.
Okay.
6.3 is volumes by cylindrical shells.
Okay.
So
when you do volumes of solids of revolution, you have to figure out how to chop your solid up and into what shapes. Because the concept is exactly the same. Instead of adding up rectangles, which is what we do to find the area under a curve, we're going to add up the volume of a bunch of discs or washers or cylindrical shells. And the cylindrical shells are the really tough one to understand. Discs and washers are fairly straightforward. But so your test tomorrow, is it on 6.1 or 6.1 through 6.3?
6.1.
Just 6.1. So just areas between curves. So that's what we should focus on tonight, or are you pretty good with that?
No, that's what we should focus on tonight, I think.
Okay.
Good starting point.
The only real difficulty with areas between two curves is if you want to integrate it along the y-axis, which you sometimes do if you have a certain type function. I mean, if I've got these two functions, I clearly want to integrate it along the x-axis because I can break it up into rectangles that are perpendicular to the x-axis. But if I have a function like this, or relation, and I want to find the area between those two curves, it makes more sense to break it up into horizontal rectangles and sum those. And whenever you're doing area between two curves this way, you want the right curve minus the left curve, and you're going to integrate from the low point to the high point along the y-axis. Now, in order to do this kind of problem, these functions need to be functions of y, not x.
Right.
So if you're given a function of x, you might have to turn it into a function of y if you need to integrate along the y-axis. I'm getting a message that I might be experiencing a degraded audio quality. I'm going to turn my camera off, which usually helps that problem. Better that you can hear me than see me.
Yeah.
All right. Do you have a specific problem that you don't know how to do on areas between curves?
Well, let's see. So I had one here that is, okay, so it's just sketch the region enclosed by the given curves and find its area.
Okay.
Y equals x cubed and y equals x. So you just set these two x's, x values, I guess, equal to each other first.
Well, that will tell you your limits of integration. Here, let me do as good a sketch as I can of this thing. I think that's relatively correct. So we know we want to integrate this enclosed area, and we want to go from here to there. But we also know that if we really want to do this in two steps, because notice that the top curve to the left of the y-axis is x cubed, and the top curve to the right of the y-axis is x.
Right.
So we wouldn't be able to take one complete integral and do from this point to that point. We're going to have to break this up into two. Right. And in order to find our limits of integration, we set the two equal, because we know where x is equal to x cubed are these points right here.
Mm-hmm.
So x cubed equals x. How do we solve that?
Move the x on the right over, equals 0.
And
then factor out an x.
And then,
okay, so x equals 0, x equals 1. Oh, okay, yeah.
in other words, I'm going to keep factoring this thing, even though we didn't really need to factor that to get the plus and minus 1. So there are 3 points, -1, 0, and 1, which is this point, and this point. So we're going to integrate from what limit to what limit in the first step?
Well, I guess -1 to 0.
Right. And which function goes on top? Or not on top, but on the left?
X squared.
X cubed?
Or x cubed, yep.
Okay, minus x. In other words, that will give you the region right there. And we don't.
You can also do it just multiplying that by 2. Right?
Yes. As long as you have symmetry. In other words, as long as you're sure that it's symmetrical about the origin, which this is, then we could just find this area and multiply it by 2. Or we could add, going from 0 to 1, of x minus x cubed dx.
Yeah. Okay.
Okay.
All right.
You want to do that integration, or are you comfortable with your integrations? And
yeah, we might as well go through that.
okay, so we're doing this integration. Okay, what's the first step?
Okay. So the integration of that is 1/4 x to the 4th.
Yeah, the way I usually do the power rule on integration is I add 1 to the exponent first and then divide by the new exponent.
Okay. Yep.
So this would be add 1, divide by the new exponent. And we're going to evaluate this thing from -1 to 0. Okay, how do I evaluate it at 0?
You just plug in the 0.
Okay, so 0 on my left, and then let's evaluate it at -1. So if I plug in -1 for x, I get 1/4 minus 1/2, which is a negative 1/4, which becomes positive, multiplied by 2, there's our area.
Okay, cool.
Okay,
Right.
and we don't need to concern yourselves with whether we are below or above the x-axis in this. In other words, you know, if you're finding the area under a single curve, if I want to find the area here, well, if I integrate the whole thing, this is going to come in negative, this is going to come in positive, so they will cancel one another out. They tend to. So if you want the area of the whole thing, you got to go to 2 points. You got to go from there to there and then from there to there and make sure that this is a positive value. Well, when you're finding the area between two curves, you don't need to worry about any of that. It's just, it doesn't matter whether it's above or below the x-axis. You want the above function minus the below function.
Okay.
Okay? In other words, I didn't care that that was below the x-axis. I'm just looking at it, and I know the above function is x cubed, the below function is x.
So does that include some sort of absolute value?
It would if you had a function like this, and you were only doing, in other words, as long as you have two functions, you don't need to care about it. But let's say I had a function that was like this, and I wanted the area between the y-axis and over here. Well, I could get it in one step if I want to integrate the absolute value of this function. In other words, if you're putting it into a calculator, say you're going from 0 to 4, then you can do it in one step. If you use the NINT, numerical integration function on your calculator, or if you use Wolfram Alpha or anything like that, any mechanical integration, then you can do it using absolute value, because it's going to give you the positive value of that. It's going to essentially turn this curve into that.
Yeah.
That's what the absolute value of that function would look like, and then it just finds that area. So you can do it in one step using absolute value. But if you're doing it manually, I usually do those in 2 steps. It's too hard to figure out manually the absolute value.
Okay.
Not sure how to do it, in fact. I guess you have to figure out where it's positive and where it's negative, which is the same as doing it in 2 steps. So
yeah. Okay.
What else you got? You got anything?
The,
You got anything
the
that
next one,
requires integration along the y-axis? Have you done any of those?
I haven't. I'm not sure whether that's going to be something I need to worry about for tomorrow or not.
Let's not cover it. If you don't need to worry about it, let's not do it.
I'm not sure.
Yeah, let's go ahead and go over the problems you have. And if one of
Yeah,
them...
I'm not even sure I see it in any of the examples in the chapter anyway.
I can give you the classic example is that one. And the reason this is a two-step problem when you integrate, in other words, this is one function, this is the other function, so we're looking for this area, but if we have to integrate along the x-axis, we've got to do it in two steps. We've got to do it one step by just taking this top function, finding the area from this point to this point, and then we'd have to do it in a second step, taking this function minus this function, going from this point to this point.
Right.
So that's how you would find the area between those two curves. But if you notice, I'll just point this out in case you have it, if we break this thing up into horizontal rectangles, now I can do the whole thing in one step. I can do the right function minus the left function, integrating along the y-axis from there to there. So there are certain functions where it really does behoove you to be able to integrate it along the y-axis, because you can do it in one step instead of two.
And pretty much you just are using...
You need to define both of these functions as functions of y.
Yeah.
In other words, if this particular function was given to you as y equals x minus 5, this one here, well, you would have to redefine it as x equals y plus 5, and this becomes the function that would be the right function, the function on the right. And you would do the same thing for this. If that was given to you as a function of x, you need to turn it into a function of y. Sometimes that can be done easily, sometimes not. In other words, this case here, I can turn it into a function of y very easily, but if I give you something like this,
right, yeah,
turn that into a function of y. It's not so easy. I don't even know how to do it. I cannot solve this for x, at least not without extraordinarily difficult maneuvers. So a lot of times which way you integrate, and this is going to apply when you get to volumes of revolution also, is determined by your ability to define the function as either a function of x or a function of y. When you get to cylindrical shells, you can solve pretty much every problem using either a disk or cylindrical shells, but one is more suitable for functions of x, one is more suitable for functions of y, and it can be vice versa also. But so this being able to define a function as either a function of x or y is very important.
Okay. So the next problem is evaluating the integral and interpret it as the area of a region.
Okay.
So it's the integral of -1 to 1.
-1 to 1.
Yeah.
Oh, excuse me. Those are the limits of integration. I was trying to figure out what function that was. Okay, go ahead.
And then it's the absolute value of 3 to the x minus 2 to the x. And both of those are inside the absolute value, and then dx.
Okay. So we need to evaluate this, or we need to figure out what it represents graphically?
Both.
Okay. Let's do the graphical part first.
Because it also says sketch the region, so
All right.
I think I have a graph of it.
Well, I'm going to do a rough approximation here.
Yeah.
The graph of 2 to the x.
It's just less. Yeah, okay.
Okay. And they want to go from -1 to 1. So they want the area and the absolute value takes care of the fact that to the left of the y-axis, the 2 to the x is on top, and to the right of the y-axis, the 3 to the x is on top. In other words, that's equal to that function, but y equal 2 to the x is equal to this one here.
Okay.
So by making it absolute value, we're going to get the net area similar to that other problem I was describing. All right, to evaluate this without using a computer, I'm going to break it up into 2. Let's see where I can write this. I'll write it right here. So I'm going to go from -1 to 1 of 2 to the x minus 3 to the x, -1 to 0 dx plus from 0 to 1, 3 to the x minus 2 to the x dx.
Okay.
Okay? And that will give me the same thing as this. Now, I can certainly do this in one step if I want to put it into net. But in terms of doing it, I don't know how to do it in one step without breaking it up. Because to the left of the y-axis, you have a different function on top than the right of the y-axis. Okay, can I erase my graph here while we evaluate this? Okay, what's the integral of 2 to the x? Or what's the antiderivative of 2 to the x?
Is it the natural log of 2 times 2 to the x?
Yeah. And 3 to the x?
Natural log 3 times 3 to the x.
So let's evaluate that. From -1 to 0. So what's 2 to the 0th?
1.
And 3 to the 0th?
Also 1.
Biggest thing about evaluating these things is I would use liberal use of parentheses, because when you make mistakes, it's always missing a negative sign. There are so many negative signs when you do integrals, it's unbelievable. Wait till you get to integration by parts. You'll have some functions where your solution has like 8 negative signs in it, and the biggest problem is keeping track of all of them. So 2 to the minus 1?
1/2.
Okay. So there's the answer to the first part.
Mm-hmm.
And the answer to the second part, in other words, this part over here, will be what? It'll end up being natural log of 3 over 3 minus natural log of 2 over 2 minus natural log 3 minus natural log 2. In other words, the reverse of this.
Mm-hmm.
Reverse both of the things inside the parentheses and reverse the parentheses to get this part up here. Now, what's our graph look like? Okay, our graph's all positive. I erased it, but it was all above the y-axis. I'm sorry, it was all above the x-axis. I got time for maybe one more problem if you want to do it, or if you have questions on that one.
No, I think I'm good on that one.
Okay.
Let's see if there's anything else. Hold on 1 second.
There are some other techniques when finding areas under the curve that they may want you to know. That one problem that I drew, you can use a geometry technique here. In other words, we can figure out the area of this triangle. So one way to do this would be to find the area under this curve and subtract out the area of the triangle.
Okay.
That's still a two-step method, so I'm not sure that's any better than doing it the way I originally explained, which would be using two different integrals. One integral would find this area, and the other integral would find this area. I've seen questions on calc tests, quite a few, that they want you to be able to do that geometry technique also. In other words, you can figure out the area of that triangle, and the area completely under that curve minus the area of that triangle would equal the area that they're looking for, the shaded area.
Right.
Now, that's the only other complication of areas under curves that I can think of, or consideration, I should say, maybe. Well, Dominic, I got a 6:45 appointment that I have to get to, so I'm gonna let you go, and I hope I've been helpful to you.
Yeah, very much so.
And I do. Let's see. Can you give me your email address, and I will send you this recording, so you can see how I record all my online sessions, and you get a copy of the file. It'll take a couple hours to process it, but then I'll send it to your email. I'll send you a link to it.
You should actually have my email.
Well, I know you put it in on GoToMeeting, but believe it or not, they do not give it to me. I mean, I have to go to quite a bit of effort to find that.
Well, you replied to my email.
Ah, I have it that way. Yes. Excuse me, I forgot. I do have your email.
Oh,
yeah, okay, so that's the one you want me to use, is that one?
Yeah.
Okay, and I will send you it'll be a link to the video. And the video just shows shows whatever I wrote or whatever we were looking at on my computer screen and the full audio. It doesn't have the webcam as part of it. But and it's like a YouTube video, so you can pause it, fast forward it, rewind it. But for complicated subjects, I think it's pretty useful because you're going to want to review periodically. And do you know, I've told you how to schedule a session. If you want to schedule a future session, you can just do it directly on my website. You can also email me if you prefer to do it that way.
Okay.
Okay. Well, good luck on your quiz tomorrow, Dominic.
Thank you very much. Appreciate it.
Sure. Bye-bye.